Hello and welcome back. Welcome back to this YouTube channel. So I took a leave. So I have not been uploading. I think for the past week. So the reason is we went to a vacation. So from now on, I'll continue to upload videos. And I'll continue to for this series at least we're going to learn more about language models and trying to understand what is ChatGPT and all that. For this series, we're going to solve some language problems. All right, so fun for this. I thought maybe we could just recap like transformer encoder and decoder is actually a very important. Like it is the like if you look at the current deep learning technology, this is probably one of the most useful and useful neural networks. Transformer neural network. So therefore, in order to make you more comfortable with working with that, to actually build and understand what is going on, understand what is going on, we are going to revise, and then we are going to build this transformer again from scratch, and then after that we're also going to solve different problems such as text summarization, question answering and all that. So let's get started. Okay, so first, before, I want to just um, make some things clear for you. So in the last video I have talked about masked multi-head attention also. I want to elaborate a bit further because I don't think I have multi-head attention. So I don't think I have given much clarity on this. So like I have also told a mistake that we'll use masked multi-head attention in the encoder layer. So in the encoder layer, we'll use masked multi-head attention. That is a mistake because no, we don't use masked multi-head attention layer in multi-head attention in encoder layer, because the ideal purpose of this masked multi-head attention is to actually hide the next word. So essentially, the goal of the transformer is actually to predict the accurate next word. But the masked multi, right? That is the goal of this transformer. So what we'll do is in the encoder, where the output will actually be generated. So in the encoder, encoder, the main function of the encoder is to actually understand the input better, and to actually make sure we are just going to update this knowledge parameters. So we'll be having knowledge parameters about this input. So we're going to update them such that more information is actually carried for the decoder layer to actually predict better. So therefore, that is a function of encoder. So in the decoder, we'll take the outputs generated by the encoder. The learnings that have been done in the encoder, we'll use these patterns, and we'll use these recognized patterns to actually predict the output. So in the decoder, while we are training, let's say we want to predict a sentence. Let's say the sentence is, "My name is Joel," right? So the model correctly predicts the word "my," right? So we have a training data set. In that training data set, that the correct statement is, "My name is Joel," the current output, let's say. So the model predicts the first word, and based on that, it should predict the next word. So given the word "my," the model should predict the next word, "name." But if we did not perform masked multi-head attention, the model will cheat, right? In the training, while training, the model will get access to the um, actual output. So the model might cheat by looking at the next word. So that is masked multi-head attention. So that is a mistake. I'm really sorry. So we don't use that in encoder. There's actually no use, because in the encoder, we're actually using the input sentence, right? We want the model to be actually, uh, we want the model to actually be aware of all of this, all of the words, all of the word embeddings, right? So all of the relations between the word embeddings. That is something that I want to make clear for you. So we don't actually use mask multi-attention. There is actually no need to use mask multi-attention in the encoder layer. So that is the idea. And then again, I'll just revise the topic. What is an encoder? So what is the architecture of encoder? So that is we're going to have the input sentence, right? So this is the encoder. And then we're going to have some weights that are passed to the decoder. We're going to have the output embedding, and then we'll generate an output. And this will be the, so this is actually loop. So in there, while training, that's right. While training, we'll have inputs and outputs. So we're going to give the input, The decoder will take the output. It will generate a word. It will take that generated word as the input. So it'll just take that word again as the input, and it'll predict the next word. It'll predict the next word, and so on. That is actually how uh, uh, like transformer works. Input output transformer. So that is the idea. So encoder, what? So we'll be looking at encoder. We'll be coding. We'll be like actually implementing encoder in PyTorch. So I also want you to be comfortable with PyTorch, because PyTorch is a library in which almost all of this research work is actually done in PyTorch. I don't know why, but like if I went to any prepper and search for any implementations, all of them are in PyTorch. So therefore, PyTorch is a very good library to learn. It is also a neural network library, right, with which you can develop neural networks. So you'll have already pre-written code for optimization and all that. So you can easily use neural networks. Yeah, you can implement neural networks through pre-written code. So that is PyTorch. So we'll be looking at encoder. So what does this encoder consist? So we are going to give some inputs, right? So we're going to have word embeddings. We're going to add positional encoding, right? We're going to have positional encoding, which just carries the positional which carries the positional meaning, or positional information for each word. Right? So we had this positional encoding, and then after we add positional encoding, we are going to give this output to a multi-head attention. We're going to perform multi-head attention. I already made clear what multi-head attention is. I've already made clear what multi-head attention is. And after we perform multi-head attention, we're going to have residual layer, right? We are going to residual connections. We are going to add and normalize. So we're going to perform standard normalization, subtract the mean and divide by the standard deviation. And then we are going to have the class normal simple fit for neural network. And this outputs will be given to this decoder. So that is actually how transformer performs. Very simple, yet a little bit complex architecture, right? So we are going to have this multi-head attention. I'm going to revise what is multi-head attention is. So let's get down. So let's say you have word, right? So let's say you have different word embeddings, right? You know about word embeddings, right? Word embeddings are nothing but representations that are optimized during training. So we're going to have this representations, and then we're going to optimize these representations based on, we are going to have similar words having similar word embeddings. So we will make sure to do that. So yeah, we are going to have similar words are going to have similar word embeddings. So right, so we are going to get some words, right, as the input, and then what we are going to do is for each word, right, we are going to multiply that. Sorry for that. Right, each word we are going to multiply by WQ. Yeah, WQ, K, and WV. So there are some weight matrices. Already probably know about weight matrices if you have been following me or have been in the deep learning field. So yes, these are weight matrices that can find you some patterns. You're going to update that also in the process of gradient descent. So we're going to take each of this sentence, each of these words. Sorry. So we are going to have n number of words. So we're going to take each number of word. So each word, and then we're going to multiply that by WK. Right. So let's say we are going to take this word embedding. We are going to multiply that, and then we are going to get Q. We are going to take this, multiply that, and we are going to get K. And then we are going to multiply this, and then we are going to get V. So what we are going to get is we are going to get some form of representation that can be useful, or sometimes some form of values that may be useful for the model. So we can actually interpret what they mean or what they actually represent. We can actually interpret them because they are the computer defines them. The computer actually finds them, and the computer will update them based on what it requires or based on what works. So therefore, we can actually represent we can actually understand what they represent. But these values will be formed. We are going to do that for each word. So for each word, we're going to have query, key, and value. And then on top of that, multi-head attention is nothing but we're going to have this multiple keys, multiple queries, and multiple values. So we're going to have multiple. So these are just one set, right? So we're going to one set of weight matrices for one head. So this all this WK, WQ, WK, WV are for one head, and then we're going to have multiple heads, and then also we are also going to have multiple encoders. I'm going to talk about that again. So we're going to have multiple heads, and then we're going to perform all of these keys for all of these words and for all of these heads. So therefore, it is a very huge matrix, right? And then we are going to perform this Q, K, and V. And after we have performed this, what we are going to do is for each word. So let's say for this word I, we are going to multiply this Q. So the query vector of I will be multiplied by, sorry, will be multiply that by the key vector of the next word, let's say. So let's say we have two words only. So we're going to find the relation between these two words, the attention of these two words, and then we're going to multiply that by V, right? And then we're going to perform the softmax, and then we're going to divide that by square root of dk, which is nothing but the dimension of query and key and value. So we are going to get the dimension. So one, like how, like it is a matrix, right? It's a 2 by 2 or n by n matrix. We're going to find n, we're going to find the square root, and then we'll divide. So what is the idea is? The idea is nothing but for each word, we are going to have this query vector, right? And then we're going to multiply this query vector. I've already told you how query, key, and values vector come from. So we're going to multiply this query vector with the key value or key vector of this next word, if you want to find the attention between these two words. So we'll do that for each and every word. So we are going to do for this word with this attention, and if there are more words, we are going to also calculate the attention between this word and the corresponding next words. So that is the idea of attention, right? So that is how attention mechanism works. Now let's try to go to Google Colab. Right, let's go to Google Colab, and let's start coding. Let's start implementing it. Let's start. I'm just going to I'm going to code, and we'll be learning step by step, like what each and everything means. Right, so it's just going to take some time. Sorry. Okay, sorry. Yeah. So first, let's just rename our notebook. So this is a notebook, right? So let's just rename it to, I don't know, some name. I'm just going to remove this, please. Okay, sorry. Hello, 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 hello. Okay, so can you please, hello, hello. Yeah, sorry for that. I just disconnected my microphone. Right. I'll just plug in my mouse little quick. Good. All right. Sorry for that delay. I want yeah. Yeah, good. So now I'll just rename the notebook. I'll just rename the notebook something as Transformer Encoder, or yeah, I'm just going to say Transformer, or let's say Transformer Part 1, right? Just for fun, right? So Transformer Part 1. So we are going to do Transformer Part 1 now. So we have renamed a notebook. So first let's just import the necessary libraries, the libraries that we might require. So the required libraries are Torch, Math, to perform mathematical calculations, mainly for finding the square root, I believe. So we are also going to import uh, the NN library from Torch. So it's actually another like it is the key, in TensorFlow you have T have TensorFlow dot keras dot layers, right? So just like that, we are going to have subfolders or sub files. So in this or in this class or in this file, yeah, or in this main in this main set of files, I should say, in this main set of files, we're going to have multiple files, let's say, or multiple functions. I don't think, yeah, I think this is a file, or could be a class. I don't know. So in this, we're going to have multiple functions and multiple classes. So that is how you will just implement the NN library or NN subset library of PyTorch. Torch. And then we're also going to import um torch.nn functional, which is, you know, sorry, torch.functional. Sorry, it's actually torch.nn.functional. Actually, yeah. So we have imported the necessary libraries. So these are the libraries that you will require while coding a transformer layer, right? So like in TensorFlow. So in PyTorch, right? And then now let's first, as you might have guessed, we'll first build the function of scaled product attention. You know about scale dot product attention, right? So we are just going to do we're just going to find QKV values um one by one, right? So we're going to find QKV values one by one. So I'll just say scaled dot product attention. That's a huge name, but no problem. So the inputs are QKV. So we are not actually building any um like torch, like we are not actually building a neural network here. We're just going to do the multiplication, right? So actually the classic multiplication that I've already showed you, right? So we are not actually not going to require a mask, right? We're going to do scale dot product attention. So what should we find first? Well, we should find the DK, right? So we are, as I've told you, after we have multiplied, after we have multiplied by QK and V, and also after we have applied softmax, we are going to divide that by DK, right? So DK is nothing but the dimension. So to get the dimension, oh, sorry. Yeah, so we are going to find DK, right? So to get DK, to get the actually the dimension, we can actually do something. So you can just say Q dot size. You can just get the -1 size. That's a -1 in the nothing but we like in a matrix we'll have n by n matrix. So to get n, we'll just use this simple Python trick. So and then after we have find the DK, it's now we can just find the scale dot product relation, or we can just find the dot product of Q and K. For that, to actually find the dot product, we'll have a torch function called matrix multiplication. So we'll actually find the matrix multiplication between Q and K, the query vector and key vector. So we'll find that, and then right. So we're going to find the query vector, the multiplication of. So we're going to multiply query and key vector. As I've already told you, why we'll multiply. I've already described everything to you, and then after we have done that, now we can just say math dot square root of dimension K. So, or you can say dimension Q or anything, right? Right. We are just going to do that. So we have right from now until now we have done nothing. We just find the scaled or we just find the matrix multiplication of Q and K, the query and key vector. And after that, the next thing is we'll just multiply that by V. So we should first perform softmax, and then we should do multiplication. So what I'm going to do is I'm going to say f dot softmax. So f is nothing but torch dot nn dot functional. So we're going to say f dot softmax of x of scaled. Sorry. So we're going to perform a softmax on scaled. And after we have performed this attention, we're just going to multiply that by the v vector. So I'm going to calculate, we're just going to multiply this attention vector with v. So I'm going to say torch dot mat multiplication again, matrix multiplication. And then we're going to multiply attention and v. And then after that, we can just return the attention. This is just like simple step where we get the q, k, and v values, right? So the input is q, k, and v, query key and value, and then we're going to multiply that q and k, divide that by dk, and then for have the softmax, and then multiply that by v, and then return the attention. So yeah, so we just build this function. So this function is actually ready. Now let's get to this main part. We have to first find this q, k, and v. I'm actually going to show you how we can find q, k, and v, how we can like build TensorFlow layer, or sorry, Torch neural network, such that we can actually create this updatable parameters, optimizable parameters of q, k, and v. Right. So we're going to have let's build the multi-head attention layer. So we're just going to create a class of called multi-head attention, and then I'm going to inherit this class from torch from nn dot module. So what this enables me to do is, so in this class, I could actually, like this class can all, I think it can be seen as a layer. In TensorFlow, you have tf.keras. Sequential layer, right? So just like that, you could create layers here, like torch layers, and then you actually have this updatable parameters. So it's actually, I think it'll actually train the layers that have been defined. So we'll do that. So first we should create the init function to actually initialize some things. So what will be the output? What will be the input? So it inputs are nothing but d model and number of heads. So I'm just going to go there and tell you what d model is. So for that, I might just need my board. Right. So what is a d model? Sorry for that. So I have told you that we're going to have vector. So we are going to have query key value vector. So, and then after that, to actually calculate it, right, to actually do it in code. So in theoretically, what we'll do is, I have explained you that we are going to have q, k, and v separate vectors, but in practically, when you are actually implementing this attention or transformer neural network, what we'll do is, you'll actually create a combined vector. You actually output a combined vector by this neural network, which contains of q, k, and v. So we are going to have q, k, and v combined in this output. So we don't have q, k, and v combined output by neural network, and then we are going to split that again. And not only this, as we are performing q, k, and v for multiple heads, right? So we're going to have multiple heads. So what we are going to do is, we are going to do that for different heads, right? So we're going to have, let's say we have two heads of q, k, and v vectors. So we have two layers. Sorry for this box. I want to confuse you. There are actually three boxes only. 1, 2, 3, 1, 2, 3. So two heads, two layers of q, k, and v values. So two separate weights, I should say, or two separate outputs, which are all combined in this here. So what d is actually? D is nothing but I think the shape, right? So d is nothing but the, like, it is going to matrix, like it actually defines something about the, like it is the shape of this matrix, like d model by d model, right? And then after that, I'm going to, after I initialize this, I'm going to initialize some variables that we are going to use in this class. It's nothing but self.d model equals d model. I'm going to do that. And then self.number of heads. Number of heads. All right. So we're going to have, we're going to also initialize number of heads. It's a number of self dot number of heads equals number of heads. And then now let's initialize our layers. So what are all the layers that we are going to use? Right. So we are going to have a QKV layer. QKV layer is nothing but the layer in which we are actually going to calculate the query key and value vector. So the inputs are going to be nothing but the X, right? So the input is nothing going to be X, which is actually D model, right? And then outputs are 3 into D model, because we are going to have calculate the vectors for all of these 3 query key and value vectors. So we are going to have something like this. I'm going to do this and then layer. So we're going to build a TensorFlow layer. Oh, sorry, a PyTorch layer. Like this is how you define a dense layer, like you do in TensorFlow. You're going to have D model by 3 into D model. Right. So the input is going to be the size, the shape of D model, and then the output will be equal to 3 into D model. Why will you do 3 into D model? Because we'll calculate the output for all of these query key and value vectors, and then we're going to separate the separate the big like this. We're going to separate this output matrix into query key and value matrix. And then after that, we are also going to do this to actually calculate the head size or head dimension or head dim. We're going to have to calculate the head dimension, which is for each head. Right. So we are going for here, D model is nothing but the total overall shape for all query key and value for all the heads. And then what head dimension is nothing but the shape for each head. So to calculate that, you might have guessed it. It is nothing but D model divided by the number of heads. So we're going to have this combined shape, and then we're going to divide that by the number of heads. So for each head, how many? For each head, what is the query key vector? Query key value vector shape is going to be, or dimension is going to be. And after that, we'll also have to calculate the like another linear. We are also going to have another linear layer, right? So in the multi-head attention, we are also going to have the last linear layer, which will give the outputs to the to actually add and normalize. So we'll have this another linear layer, right? Sorry, it's actually linear. It's not layer. It's linear. Linear, not linear. So here the output this is going to be D model. This is going to be, sorry for that, D model by D model. So we are going to get the output as input as D model, because we'll already be dividing the QKV matrix into separate streams, right? And then after that, we are going to give each, like we are going to have D model by D model as the input and the output. And after that, let's do the forward function. Forward is nothing but, if you are implementing in I think PyTorch, you actually have to define a forward function. And then I will have the self, and then the input is X. So in forward to actually carry it, we need X. So we're going to carry these layers on this X. So after we do that, let's calculate the input dimension. So what will be the input embedding? So input embedding of X. So to actually calculate, we're actually going to calculate the input dimension of X. So what is input dimension of X? Well, I can just say, right. So we should also calculate the like sequence length. So we the input is going to be a sentence. So we'll see X is going to be a sentence. So first we'll determine how many number of words are there, and for each word, what is going to be the input embedding dimension. So to do that, I can just say the sequence length, comma, right, comma, let's say the dimension is going to be equal to X dot size. Right, the sequence length, we are going to extract the sequence length, the number of words, and each and the embedding dimension for each word, we're going to extract these values from X, right, through this operation. And then after that, we'll perform the QKB, where we'll actually going to obtain the QKB values into a combined matrix, of course. So what we're going to do is we're going to say QKB is equal to self.QKB layer. We're going to call this already initialized variable, and then we're going to do it this on X, right? So by given X, so we're going to actually input this value X, and then we're going to have this multiple weights, multiple QKB weights. Like, I'm just going to go through the whiteboard just to make sure it is clear for you. Sorry for that. So yeah, we are going to have QKB values, right? So what we are going to do is, given the input, we'll take the input X, right? And then we, for each head, we're going to have QKB values. So let's say we have two heads. We are going to have QKB values. So how are these values instated? As I've told you, the output layer, like the output number of output neurons is actually equal to the number of outputs. So therefore, we are the number of neurons in the NN dot layer will actually determine how many, like what is the dimension of the huge weight, or the combined weight of all the QKB vectors, right? And then what we are going to do is we are going to multiply this X by all of these values, right? Or WQ, probably WQ, just for your understanding. So we are going to multiply WQ by X, and then we're going to obtain Q1. Let's say we're going to obtain K2, K1, and then V1, right? And then we're going to multiply that X by WQ2, and then we're going to obtain Q2. So we are going to have multiple weights. And then what we're going to do is, in this neural network, we are going to take in X, and then we're going to multiply X by all of these weight matrices. And then we're going to get this combined matrix, the combined matrix of all of these values, query key value vectors for all heads. We are going to get this combined output in the program. And then after that, we are going to divide that for each of these query key and value vectors. So to actually now what we have to do is we have to, let's just reshape it. We just say QKB dot reshape into, so just listen, we'll actually reshape it very simply. So we can just say sequence length by right, number of heads. So we are actually we're going to have this combined matrix for all the heads. We're going to have this combined matrix. So now we are going to actually divide this matrix into self dot number of heads for each heads. So we're actually going to have row column structure, something like row column structure. So for each sequence select, we are going to have some number of heads, right? For each sequence length, we are going to have some heads, and for some heads, and for each head, and then for each head, we are going to have 3 into self dot head dimension, head, right? Right. So why 3 into? Well, again, query key and value, right? So we're going to have head dimension, which is nothing but the combined matrix of query key and value for each head. So we're going to multiply that by oh, sorry, not the combined. So we're going to have this self dimension, head dimension, right? So we're going to have this head dimension, which is nothing but the dimension for each head, and then we're going to have 3 into head dimension. We're going to multiply that by 3. And then after we have reshaped this query key value vector, now what we can do is, so I don't think we need a 3 here there, because because D model is actually going to consist of all query key and value vectors. So when we calculate the head dimension, I don't think we need 3 into there. We don't need 3 there, right? So we're just going to have self dot head dimension. My bad, sorry for that. Now let's divide this query key and value vector from this matrix of QKV. So what to do that? I can just say QKV dot chunk and put 3 in there. No, I think 3. Yeah, that's it. We'll actually be dividing this QKV vectors into like QKV vector into or matrix into separate matrices. Now we can actually calculate the attention. Attention is nothing but scaled dot product attention. We're actually going to call this function inside this class. And then what are going to be outputs? QKV. So simply we are just going to calculate the attention between these three specific QKV values. Right. So for each value, we are going to actually going to calculate this QKV values. And after we have calculated these values, we are going to reshape this attention layer again. So just to like I'm going to we're just going to combine all of this value heads into a single thing. I'm just going to show you what's going to happen here. I'm going to say attention dot reshape. I'm going to reshape this attention into sequence length by, so we're going to have sequence length by self dot num heads, and then we're going to multiply that by self dot head dimension. Why are we going to multiply that? I'm just going to say because so after I've actually showed you in the attention mechanism, sorry, attention paper, in the research paper of attention is all you need. After we have calculated the attention for all heads, so we're going to have multiple heads, and each head is going to calculate an attention value for each of these layers. So the reason for adding multiple heads is actually to extract many features. So after we have calculated this attention for each head, for every head, what we are going to do is we are going to combine these heads. So we're going to combine all of these heads into a single matrix, right? So we're going to combine all of these heads into a single matrix, and then we are going to send that to a neural network. That's a simple neural network, and then we're going to get that output, which will be definitely be the output of multi-head attention. So what I'm going to do is after I have calculated this, after I have calculated this attention, I'm going to send that to a I'm going to send that to a, or I'm going to output. Output is nothing but self dot linear layer. I'm going to send that to a linear layer, right, of attention. Hope you understand what is going on here. So the process is actually very simple, right? So you have yeah, the shapes are confusing. The matrix shapes are a bit confusing. So for that, I really recommend you to check a linear algebra series, matrix multiplication of that, of 3 blue 1 brown. 3 blue 1 brown is a YouTube channel. Make sure to check that out. To understand the shapes better. So yeah, it's actually very simple. D model is nothing but the overall shape of all query key value vectors for all heads. And then we're going to have QKV layer, right? Output is going to be 3 into because yeah, we actually, sorry for that. Yeah, we're actually going to have 3 here. Yeah, we are not actually going to have 3 here because not here. Yeah, we're actually going to have 3 here because D model, I have confused. Sorry, D model is nothing but we are actually going to have D model for each vector. So for query vector, we're going to have separate D model. For D model by D model matrix, by for key vector, we're also going to have the same matrix, which will be optimized. So that is the idea of multi-attention. So we have actually built the main part of this video. Now let's build the layer normalization. There is actually layer normalization in this attention mechanism, right? So we'll just go faster. Layer normalization. I'm just going to build this class. So it is actually going to have TensorFlow NNR module. And then let's have this initialization layer, init layer. And then the self parameter shape. We need parameter shape here. I think that is the only parameter we are going to need. Input parameter we are going to need. That is the only input we are going to need. And then we are also going to have epsilon, which is nothing but a very small number. Let's say 1e minus 5, but 1e5 because we will be leading a very small number. Just to make sure that we don't get divide by 0 error, right? Division by 0 error. So we are going to do some initialization. We're going to say self dot parameters, parameter shape. We're going to be parameter shape. right? And then we would have self dot epsilon is epsilon. And after we have done that, we are actually going to have some more uh, trainable weights. I'm going to talk about that also. So we're going to have nn dot parameter. So this is actually function. So this is actually a weight that it can be that will be optimized, right? So we're going to have nn dot parameter and then torch dot once. So here I'm going to create a weights. So I'm actually going to create a matrix of ones, only ones in the shape of parameter. Why am I creating it? Well, it's just the initialization state. So while you are optimizing it, for the first time, you want to initialize randomly. So for this initialization, we'll actually going to have ones, and then we have beta, and then dot parameter, dot once, parameter shape. And then we're going to have this main feed forward function. So a forward function, self x inputs, anything like that. So what we're going to calculate is first we'll calculate the mean. Mean is nothing but input dot mean, right? Simple. And then we're going to have this calculate the standard deviation. Now let's calculate the standard deviation. Standard deviation, which is nothing but we have a simple formula here. Mean minus, sorry, input minus mean. Inputs minus mean, right? So we're going to calculate the square root, right? We're going to calculate the square root, and then we're going to further calculate the mean, right? So this is the formula to actually calculate our standard deviation. And then we should also we should also add epsilon. Yes, let's add the epsilon, and then we should also divide by, right? We should also divide by the square root. Now we're actually going to find the square root. So it's like self dot epsilon. Sorry for that. Right. So we're going to find the standard deviation. And after we have find the mean and the standard deviation, we're going to subtract by the mean and divide by the standard deviation. So it is going to be like this. So y is nothing but inputs minus the mean divided by the standard deviation. And after that, I'm going to calculate the output, which is nothing but y is going to be y into self dot gamma plus self dot beta. So they are going to have this self parameters, some optimizable parameters, which we are going to multiply by y and add to beta. So and add, right? And then after that, it's going to return the output. So that is a real layer normalization. Now after we have built a layer normalization step, right? Now we have built a layer normalization step. Now it's time for us to actually implement the positional feed forward neural network, which is nothing but a simple feed forward neural network, right? I'm going to say feed forward. We're going to say feed forward. So we are going to inherit from nn dot module, right? So we are going to have init self, and then what are the inputs? The model, the hidden layers, number of hidden layers, and then dropout probability. What is going to be the probability of dropout? So how many neurons are we going to drop out? And then we have, let's just initialize some layers. And then dot linear, D model, hidden. Again, we're going to have self dot linear 2, which is again going to be nn dot linear, hidden, and then D model. So hope you understand. The first parameter is actually the input. What is going to be input, and then output here is actually going to be this output, right? And then we're also going to calculate the where we're actually going to have the ReLU layer, and then dot ReLU, right? And then we're going to have dropout layer, the final dropout layer, which is going to nn dot dropout. And then P is going to be drop. Right? So we have initialized the variables we are going to need. Now let's build the forward function. So we'll be needing self and x. So let's do this first. We're going to have this linear layer, which is going to take the input f x, and then we're going to have this ReLU layer x, and then we're going to have dropout, do that on x, and then we're going to have linear 2 on x. So this is going to be the output. So we'll return x. So this x is going to propagate to all of this function, and each function will actually make a change to this input. And then of course the parameters are going to optimize. Let's hope we understand what is going on here. We actually also build the feed forward class, and now it's finally for time for us to actually build the encoder layer. So finally we can just build this encoder layer, right? Encoder layer, the final encoder layer, and then dot model again. And then in the int function, all the required parameters of all of these values is actually going to be inputs. So like the required inputs. So what, like if you go to multi-head addition, so what are we going to need? D model and number of heads. So I'm going to say D model. We're going to need D model. We're going to need FFN hidden, the number of hidden layers, and also the number of heads, and then the dropout probability. So these are all the inputs that we are going to require. And then now let's do some initialization. Let's build some functions. Let's call the function that we have already built. So I'm going to say multi-head addition. I'm going to call the multi-head addition layer class. Right. And then the D model is going to be the D model. And then number of heads is going to be equal to the number of heads. After that, I'm going to calculate I'm going to have a normalization there, which is nothing going to be no layer normalization. And then parameter shape is going to be D model. Right. And then I'm going to have another, normalization layer. We're going to again going to call layer normalization. Parameter shape is again going to be D model. Right. And then we are going to have a dropout layer. So I don't think we need a dropout layer. Right. And then we're going to have a feed forward neural network, which is going to be feed forward. And then what are the inputs? Inputs are D model, hidden, which is nothing but FFN hidden, and the dropout probability, which is nothing but dropout probability. All right. So we're going to have all of these functions. We are going to use all of these functions. So therefore, we have initialized them in the initialization layer. Now let's build the forward pass. So what is the inputs? X with X. Now let's build our architecture, the main architecture of attention or the encoder layer. So first we're going to calculate X, residual X. So remember we had residual connections. So therefore we're actually going to store this X and I add it after we have performed some of these layers. So we're going to have so we're going to perform self-attention on X. So I'm going to say X is equal to self-attention on X. We're going to perform self-attention on X. And then we're going to add X. So I'm going to say X is equal to let's say norm1, self.norm1 of X plus residual X. Right? Understand? So I'm going to add X to residual X, and then after that, after I've added that, I'm going to have a feed forward neural network. Feed forward neural network. Right? I'm going to send this X again into this feed forward neural network. I'm going to get this output. Right? Before that, I should probably store this in the residual x, right? We are going to have another residual connection, so therefore we'll actually store x again. And after that, we're going to add x. We're going to say self dot norm 1 is x plus residual res x, right? We are going to add that again. So finally, we have this is our output, and we'll return x. So this is the encoder layer, right? So this is the encoder layer. So we have actually initialized some of these classes that we have actually previously built, and then we're going to have this combined encoder layer. Now, after we have developed the encoder layer, it's time for us to actually develop the main encoder class. It's time for us to develop the main encoder class. Like if you observe here, we actually had only one encoder, but in actual transformers, while actually building transformer, you can have multiple encoders. So the output you just input to the encoder, and then the output will be sent to the another encoder, and that encoder output can be also be sent to another encoder, and that output might be sent to the decoder. So we might have number of encoders. So therefore, to actually have the ability to actually build multiple encoders, will build another class, which is nothing but the main encoder class, which is also inherited by the NN model. And then we're also going to develop the initialization function, self, which are going to have the same parameters. So yeah, it is actually going to have the same inputs. So as you can observe here, this will be the main class, outer class. So this class will actually handle, like, observe all the inputs from the will observe all the inputs, and inputs will be sent to a particular class based on what they need. We actually code that here, right? And then we're going to have the extra parameter we're going to have is the number of encoders. So the number of encoders can actually be we actually can like change number of encoders there are. And now let's just build a sequential layer, the final sequential layer, which contains all of these encoder layers. So this encoder layer is at a PyTorch layer. We're going to have multiple encoder layers. So actually define, I can actually let's say how many encoder layers we want. So what we're going to do is, right? So we're going to have, so we're actually going to call this encoder layer on D model. So what are going to be the inputs? We're just going to extract these inputs from the user, and then we're going to send them again to this encoder layer, right? What they need, drop, and then after I did that, what I'll do is I'll just do this for all of these encoder layers. So then the number of encoder layers is actually going to be equal to the parameter of number of encoders, right? And then I'm going to have this forward pass finally, forward pass, and then I'm going to have self x, which will actually be the sentence, and then I'm going to actually pass that forward. I'm going to say x is equal to self dot layers of x, and then I'm going to return x. Oh, so therefore, we have completed it. The transformer in PyTorch, might be a little. I don't think I have explained that good, especially this part. I know, but here, listen up. I'm just going to do that again. I'm just going to say what I've said here. So we're going to have QK values here, scale or attention function. We're going to calculate the inputs are going to be Q, K, and V. So we're going to multiply and calculate the attention. And then in the class of multi-head attention, this is the main thing here. What are going to be the inputs are D model and number of heads. So we are going to initialize D models, the number of heads. We are going to build a linear layer, which is going to in which we are going to calculate the vectors for all of or matrices for all of these Q, K, and V values. So we cannot do it separately, or we cannot do it separate Q, separate K, separate V. So rather than doing that, we'll just use this method of doing like calculating every matrix and updating every matrix at a time. So we'll do that. We'll update everything parallelly, and then we'll calculate the head dimension, which is nothing but each the dimension of D model for each head. So for each head, what is going to be the dimensional shape? What is going to be the dimension? So we are going to multiply D model by the number of heads. So D model is actually going to be the combined combination of matrices for all heads. So we're going to divide that by the number of heads. And then we're going to have another linear layer, which is going to be the output. So at the output layer, we're going to have a linear layer, which will performing on the uh, output tension after scale dot product. After scale dot product. So we're going to have layer normalization, which is actually pretty simple. We're going to have gamma and beta values. After we have separated the mean and divide by the standard deviation, we are going to multiply that by gamma and add beta. So just like a simple neural network or simple neuron, not a neural network. And then we're going to have this feed-forward neural network. Again, simple classes, linear. So we are going to initialize some linear layers and value will drop out. And then finally, we'll add them all together to the encoder layer, which is nothing but we just take the input, do some residuals, store the x values, we'll perform the self attention, we'll add the residual to the output of self attention. We're going to normalize, we're going to again store that value as resx, and then we're going to perform the feed forward neural network, and then we're going to add that and normalize again. So actually, you can actually experiment with the number of like layers here. That is the good thing about implementing it yourself. So you can actually experiment with the number of maybe linear layers, or maybe in the multi-head attention function. So maybe here you might add multiple, like you might increase the model, maybe do something, maybe create larger matrices. Maybe you can experiment. You are always welcome. Definitely adding more complexity will increase the accuracy of a model. Definitely try changing the number of layers and all that. It might increase the performance. So actually, ChatGPT has many billion parameters, so they might have many encoders and many decoders. So yeah, I mean, so this is it. This is transformers, and next video we'll be focusing on transformer decoder, transformer part 2. We're going to implement it from scratch, just to make sure you understand everything. All right. Thanks for watching, and I'll see you in the next video. So yeah.